See how laggy this is. Oh, that's actually not bad. Okay, cool. So I've been here before. Everyone knows me. Yay! I'm Jacob. Settle down. Or go longer. You want to. I work in the computer science department down the street. I do things over there. I teach classes. I do a lot of mentoring of students, I guess. And today we're going to go over Golang. We're going to actually do a pretty deep dive into Golang and do a little bit of hands-on profiling and benchmarking at the end for funsies. So I asked ChatGPT, give me 300 options for a punny title for this. And out of 300, this was 177. So that's how far I got down the list till it became funny. So yay, ChatGPT.
Wow. How long did you do?
What?
How long this introduction you didn't know? How long did you?
How long am I going to stay on this slide?
Yeah.
Is this already boring you?
No, I want to just any time because.
Oh, well, I mean, all the slides I'm going to send in a PDF. So I'm going to export to PDF and you'll have it.
We're recording it.
So, and we're recording it, so yay, watch it later on while you get your second screen of anime up. Okay, so 5 things we're going to go over, 0 through 5. First thing is, what is software engineering? And we're going to go over a book I love called A Philosophy of Software Design. It's a great book, it's awesome. And it's actually recent, which is finding a recent book in computer science. It's sort of amazing. Next thing, we're going to go over language design and constructs. And then we're going to create our first program. Then we're going to go over a little bit of some modern things that goes added that C, C++, and Java really don't have baked in. Then finally, we're going to go over more of the entire ecosystem, the gold standard. Haha, more puns. Great stuff. Thanks, ChatGPT. Where we have our software testing and our benchmarking and our profiling built in. And then finally, a little bit of conclusion just with like a page of here's links to click on. Here's some YouTube channels that are awesome. Here's docs, resources. So what is software engineering? You write software. Everyone's like writing code here, right? Like everyone's written code. There's no English majors. There's no like history majors, none of that, right? Everyone's written code here. Either, through Terminal VI, VS Code, Eclipse, probably. Everyone's written code, right? But you've written that code just to get it working. You've got a problem, homework, you got a linked list you got to make, something, some assignment, and you're just writing the minimal amount of code to get this thing working. And that takes a while. Like that's a job in itself. Getting the code working so your input is the expected output. But that's just programming. That's not software engineering. At the end of this, you've created software. Like you've made a piece of software. But we got to go farther than that. Because this homework assignment that you've been working on for weeks and finally got it working, it's done. It's turned in, right? You get your solid B. Get your high B+. Or if it's migrators lately, a high C for some reason. Because they're animals. But you just like save it off in a zip file or in Git and you never look at it again. You're never going to go back and like, oh, how did I work that linked list homework problem? You're not going to look at it again, right? You may take a look at bigger projects you did in the past and like copy and paste some stuff, but it's not really the same thing. In industry, once you make this a career in your job, other people are going to look at your code because they're going to modify the code because requirements change 6 months from now. You're going to look at your code 6 months from now. So this software becomes software engineering, and it's the second set of processes that are sort of outside of you just sitting down and looking at this problem of making a linked list, right? So we need to bake in other things. And when the designers of C and C++ and Java wrote a language, they didn't really have these constraints in mind. They were working with, I need to solve a problem. How do I get this code to run on this desktop and this projector and my toaster? I'm going to make a virtual machine and make it tiny and fast, and I'm going to write Java that gets compiled to Java bytecode. Problem solved. They weren't thinking about the entire ecosystem of software development. And the things start to creep in. Version control was not around 20 years ago. People had zip files. People had, tar gzips, _final_final2, draft. People were like emailing code around or FTP code around. There were some horrible systems, like ClearCase was one of them. You would log into it, you would FTP code down, and you basically were handed a token. You can modify the code today, kind sir. And then when you're done, you hand the token off to someone else. It was a horrible system. Like, this was not software engineering. And really, testing was an afterthought. Java unit tests came way after Java was developed. For C, there's so many different testing libraries and ways to test. Most C tests become integration tests because you just sort of build a binary and then test whatever's running against it. Even, quote, modern languages that have come out recently don't really have baked-in testing. And also things like static analysis and linting. There's not a lot of good, full-blown linters for C++ just because the language is so complicated. It's hard to write a parser that's not the compiler to parse through it. And that's why things like Clang and LLVM have rose to such prominence, because those people are actually able to get it working. So all these things you're doing and looking at are past day one. They're day two. They're future you problems. And this is what software engineering is now. This is the book. There's a QR code here. It's real thin. It's like 150 pages. It's not much. And it's like 20 bucks. And it's written by a Stanford professor, really good guy, and lays out a lot of the light bulb ideas like, oh, that's the problem. That makes a lot of sense. And it's a quick read. It's good. I highly recommend it. There's a link to, I think, Amazon there. Not an affiliate link, so don't worry. I'm not getting 1 cent off of every time you click. But this book goes into complexity. If we can reduce complexity, this is going to enable us to modify code faster, ship products quicker, onboard new people. Onboarding new developers, especially early career developers, getting hands on keyboard and committing code is a metric at a lot of bigger firms now. They're competing. Facebook's down to like 12 days. We onboard a new person, their badge ink is still wet and they're committing code to a repo. And Amazon's like, oh, we're at 10 days, we're doing better. It's a weird metric, but it's true. If you can get an early person committing code, getting in there, understanding things better, they can solve problems quicker. From a business standpoint, that's a win. From a software development standpoint, that's a win. They're more engaged. They want to be there, right? But complexity is the thing that's driving a lot of these. And this is like a full 4 chapters of the book I'm compressing into 1 slide. But one of my favorite quotes from Russ Cox, who is a Googler, is software engineering is what happens to programming when you add time and other programmers. And he actually copied it from another Googler himself. But it's such a succinct way of expressing what software engineering is. You've done the program, but now you add time and other people. What happens? What happens in that time? What happens when other people start to use it? So what creates this complexity? Dependencies. If anyone's ever had to run a huge C or C++ program to get something working, like in 1040 or 2110, external dependencies start to become a problem. If we're versioning it, where are we going to version it? How do we do builds? How do we make sure every developer is making it build the same way? Oh, makefiles. Awesome. We'll do makefiles. Oh, well, the dependencies require this makefile because there's actually a version back. Okay, well, we have that makefile called that makefile. Well, you just invented Bazel, and Bazel's another beast. Bazel's so bad, now we have another tool called Basilic that manages the original Bazel install. And it becomes like turtles all the way down. So cutting dependencies off and having a proper way to version them eliminates a lot of this complexity. Stateful components. Unnecessary mutable state hinders predictability. And this is, from a functional programming standpoint, this is where my input shouldn't be mutating on the way in, coming out. The guy who wrote the book he's very focused on Java, so his idea of mutable state is different than mine, but the sentiment's the same. Over abstraction. Being a Java programmer, this hurts him a lot. Having your factory adapter, factory class create subcomponents of classes, and where does it end eventually? Am I gonna make a service eventually out of this? Is it a web server? I don't know. Over abstraction really kills a lot of your mental modeling and how much you can hold in your head. We've been taught as computer programmers to sort of decompose problems into simpler things so that we can solve simpler things and then glue it back together. And over abstraction sort of defeats that, because now we got to keep all this mental model at the same time. Lack of encapsulation. So you have a problem in C, obviously, a little bit in C++, where maybe to access this field, we need to export it. And then, well, it's public, well, it's got to be public over here too. And pretty soon we're not encapsulating this code into modular little pieces. On bigger teams, inconsistent design. You know, I've opened up a lot of Python programs where I see group members, they'll access URLs like 3 different ways. And I'm like, 3 different ways? There's only 2 members in this team. How did this happen? And now I've got to keep all 3 ways on my head of how they're doing it to sort of map around. That's a problem. Obviously, inadequate documentation. How did C++ programmers operate before C++.org was around, right? I don't know. I think they went to the library and found books, and they just had books on their desk. And then premature optimization, which, I mean, we've all heard it, but this actually hurts quite a bit. Premature optimization, when we try to make code golf, we try to make something as tight as possible. Well, in a long scheme, it doesn't really matter. We've wasted all this time, and it's so complex. 6 months from now, we need to modify it. What is this even doing? Like, now you have to unpack everything inside of it again, all that optimization you did, to figure out what it's going on inside in the first place. So these are all problems of complexity, and it's evidenced by the person here trying to keep all this in their head at once. It's crazy. Great graphic, love it. So how do we do these? Working code isn't enough. We got to emphasize readability and maintainability, not just code that works. Working code is great, but we got to go beyond it. Making deep modules. This is a real, like, one of those light bulbs, like, oh, this makes so much sense. Like when you read a paragraph of text and you're instantly like, oh, I 100% know what this means now. So deep modules are where we hide details inside a module, and the interface is super simple. Python does this pretty well. There's a lot of Python out there for machine learning, for AI, for like scikit, that does it really well. Like behind scikit and NumPy and pandas too a little bit, there's a deep module of stuff. A lot of statistics and math, but what they expose is a really nice function for just, import a model, run it. You can add more arguments if you need it, but right here is this real simple, deep module you can work with. So as a new user of this, I'm not immediately getting killed by reading through documentation and having to go through all the lines of code to figure out what it's doing. So deep modules are really important. Information hiding, public-private. If a consumer of your code doesn't need to have access to internal variables, why expose them in the first place? It's not needed. It's just going to break their mental model because they've got to load up and like, why is this var here? What is this doing? Different layers for different abstractions. Don't like slam pieces together. If we're going out to a database and going out to a web server, I shouldn't be sharing code. There shouldn't be code share between these two things. Keep them distinct and encapsulated, far apart. And then choosing the right set of modules. Prioritizing modular design to manage complexity keeps functions cohesive. So we also have a set of information error management, pulling complexity downwards. We want to abstract away complications. That's what NumPy Pandas is doing for us. It offers that user-friendly interface. Instead of silently failing, let's bubble errors up. But maybe don't make 100 errors, maybe make just a few errors. Couldn't write to disk. They don't need to know why, maybe, but couldn't write to disk. Don't just silently fail when you can't do it. Defining errors out of existence. So if a user doesn't need to know about an error, don't report it back. There's no need for it. And information should be local. So don't let information leak out of modules. If the user doesn't need to know about it, they don't need to care about it, right? So keep that local to it. And then design it twice. So everything's sort of like normal until they design it twice. So this is just emphasizing iteration in design. You know, thinking about brainstorming more about different way to do things. Because maybe you can combine your ideas and actually come out with a third better solution. Okay, that section's done. That's the software design section. Everyone good with that? Bunch of words on a screen. We're gonna get better though. So this is introduction to Golang. While you're all here, yay! So the problems of software design, and the book, the philosophy of software design, he has nothing to do with Google, nothing to do with Golang. It's just a really great book that like ties in a lot of these pieces together. But the problems at Google were software at scale. They started to buy 1 million servers and 1 million services and started to have issues with building C++ mainly. Build times were getting into the hours for deploying new internal builds of products. Dependencies were getting out of control with different teams using different versions that they would conflict. For the most time, that's okay. Like, oh, your HTTP lib is this and yours is that. That's probably okay. When you start to get into like security problems, like this module handles TLS different than this one does, then internal APIs can't even connect, and that's a problem. That's when people get called at midnight. Each programmer was using a different subset of the language. With C++, you got choices, right? You got 2011, you got 2020.
17,
Yep.
20, 13.
13, you got ANSI C if you want to be fun. So that was actually happening, and that's a major problem. Your makefile built for this will not work with that. There was a lot of duplication of effort. And then version skewing was also a problem between building. So they had a lot of problems internally at Google with building major software, and it was just building more and more. So in 2007, there was a talk by the creator, Bjornstrop, I think is his name, of C++ at Google, and he was laying out all the new fancy features that C++ was going to have. And it was attended by Ken Thompson, Rob Pike, I don't think Richie was there, and Rob Grieshmeyer was there at Google, and they were not happy with what the inventor of C++ was basically telling them. They went back to their drawing boards, literally went back to their offices and brought a whiteboard and were like, we're going to fix this. And they all were big proponents of C. They loved C. They loved the simplicity of C. And a lot of times they just yearned for that simplicity. But this was 2007. The internet's been around for a while, and they thought, hey, we can do better. We can make an internet first language, but with the simplicity of C. And they had a lot of things tackling those pain points, but also a lot of things about, we want new developers to work on this. Who are our grads coming from college? What are they being taught? Well, we're being taught C and C++. Python wasn't a really big deal back then. Neither was really JavaScript, to be fair. So they said, okay, well, it's got to be a C family language. We want our new developers to fully understand this from the get-go and not have some weird like APL or Haskell syntax they've got to work through. It's also got a mascot. The mascot has no name. It is the Go Gopher. That's all. And I think one key on the slide too is it's fully open sourced. So Google actually imports the public repo for their internal stuff, and not the other way around. It's not like, here's Google's repo. They actually import the public side and use it. So we got scalability with Go. We got familiarity with new developers. We have some modern features added in. This was the key design input. We wanted to get modern features in here. When C, C++, and Java were around, when they were created, multi-core systems weren't a thing at all. Like your server had one CPU. It had a fast CPU, but it had one. But nowadays, like my MacBook has 10 CPUs. How many CPUs does that laptop have?
8.
8. That's more than one, right? And if anyone's dealt with like multi-threading in C or C++, it's not a real fun experience. It's doable, it's just not great. Java also not wonderful, but does better because the Java VM does thread across CPUs better. But like the internet wasn't around when C and C++ were invented. It had no idea what the internet was, no idea what most crypto was. So we wanted to design a language that really had these things baked in. And finally, tooling. From years being at Google, they realized, so we can do pointers. We can't do pointer arithmetic. But pointers are how we mutate state on a variable. We pass around the pointer, and then functions can set the value. So interfaces, I mean, I'm going to go into it later, but interfaces define behavior. They don't define implementation like in Java. They define behavior of something.
Is JMap of interface in Java?
There is an interface in Java.
Yeah.
There's interfaces in every language. It may just not be named that, really. C doesn't really have interfaces. But the difference is it defines behavior, not implementation, really. We do have functions, obviously, they're first-class citizens. And we have constants, which are just const, just a const keyword. You can't const an array, a slice, or a map. Ooh, but there's ways around it. But you just can't make a constant array. Const values can be in arrays, but obviously you can just keep adding to arrays, so the array's not constant. And we showed earlier type inference. So I : = 42. Go's going to say, oh, the 42 is an integer, so I'm going to infer that I is an int. The same if we did 42.0, it would infer it's a float 64. So this is something that normally holds people up. They get confused in this one. In C++, how do you make a field public? How do you make it visible outside of that class? The public keyword, right?
Yeah.
And then the private keyword. There's another one too, isn't there? Like, it's been so long since I've read like deep C++.
Protected, but that's not.
Protected, yeah, that's what it is. But yeah, it's not really the same, but yeah. So we don't really have keywords for that kind of stuff. We don't really care about one thing. Can other packages see this field? That's it. Like, can they see it? Can they use it? And to do that, we just capitalize it. So if the first letter is a capital, it's exported. It's visible. That's it. That's the rule. Otherwise, it's by default private. And this applies to everything. Everything inside a package. Methods, functions, constants, fields. It's got a capital, exported. Otherwise, private. And this just immediately, I don't have to dig around in source code to find, hey, is this field I'm trying to access public, private, protected? It doesn't matter. Is it uppercase or lowercase? And I immediately know. So scoping is, I'm going to say normal. We go from a block to a function to a package to everywhere, the universe. Sort of normal scoping. We don't have to like play around with like hoisting like in some weird JavaScript or some other horrible stuff in Python. If it's inside a block, it's scoped. Otherwise, it's in the function scoped. Otherwise, it's in a package. Pretty simple. Preferably, we've got explicit receivers, like receiver.field. So receiver, RCVR is the package. Field is the field name. That's it. Package dot field. And we've always got to use full qualifiers for the packages. We can't do the C++ trick of like importing the namespace and like, oh, it's really us. It's not. We've always got to call it from the full package.
Uh-huh.
And we do solely by name, not by signature, which is important, you know, for the Javas. Here's how control works. So this is an if and an else. The cool thing here is we can do an initialization statement in the beginning. Let me see if I can show that. Uh-huh. So I'm doing if variable colon equal 20,000. I'm initializing money to be 20,000. Semicolon, if money is greater than 15,000, print, I'm going to buy a car. Else, I'm going to buy a bike. And then after that, there's no more scope. You can't use money. It's initialized just this scope. And we can run it. Live demo. Live demo gods, what are you doing to me? Okay, that's going to be a fun one later. Will this one win?
Are you running it online or on a local?
No, it's just local.
Oh, okay.
That's sort of weird. It's just a WebSocket. Huh. I'm going to have to troubleshoot that in a minute. So we have switch statements too. So if your if statements get a little too janky and long and you're confused about what's going on, move on to a switch statement. Switch statement has the same sort of, we can initialize at the beginning, and then we can go through cases. Poof, poof, poof. There is no fall through, like in C or C++. So if it hits 1, it's going to stop, and that's it. And then at the end, we can have a default. We can have the default really anywhere, but we can have the default, and that's just the, it doesn't match any other case, it hits that.
So there's no break, or what did it mean for what is not in?
Yeah, so normally in C, you're going to have a case statement and then a break.
Yeah.
Because it'll just keep going to the rest of the statements. There's no need for that. So it just doesn't keep going. It does its case and that's it.
No, so it's smart enough to stop on itself.
Yes. What in the heck is going on? Oh, I wonder if when we take a 5-minute break, I'm going to troubleshoot the crap out of it. So looping. How many ways to loop in Java?
3.
What about iterator too?
Yeah.
4. I count 5. I think I counted 5 one day. I think there's 5 ways to iterate in Java. C++, there's 4?
Yeah, 4 while,
Yeah.
do while.
Do one.
4 for each. Range breaks 4, so 5, 6.
Why? Why are there so many ways to do a loop? Really though, and don't even get me started on Python, because like they hide stuff and like, oh, it's not a loop, it's a list comprehension.
Yeah.
So this is another thing that people coming to Go are sort of like, I only got one for loop. Yes, there's only one for loop. But we got different ways we can use it. If we just do for and then our curly braces, have a block of code, it's just an infinite loop. What are infinite loops great for?
To crush yourself.
Servers. Because the servers run forever. So a lot of times you'll actually see server code just encapsulated with the for loop. And it's doing selects, it's pulling down, web requests or whatever it's doing, and it just loops in the for forever. It's happy. We also have our traditional while loop, which is for and then a condition, and then our braces. We have a traditional loop, which we have for and then an initialization part, semicolon, our condition, and then our post part, our I++, so to speak. And that's our traditional loop right here. Break and continue work, same as other languages, so we can do a break if we find something we like and break out of the for loop to the outer scope, or a continue if we want to continue. Oh, I know my Go mod's jacked up. I think that's what the problem I had a background thread running, figure out what's wrong. I figured it out. We do have iteration over elements. So for things like a map, a dictionary, I don't know the keys beforehand. Like I've just stuff into it and then later I want to go over it. But there's no numbers, it's not an array, how would I do it? How would I, get the keys out of it so I can iterate? So there's no real keys function in Go, but there is a range. So when I do a range, I get an index and a value, if I'm using a slice or an array, and I get a key and a value if I'm using a map. And those are the two values I get back. So I can range over things and iterate over them. Okay, do we want to take a 5-minute break here?
Yeah.
Okay, good.
Yeah.
Okay, take a 5-minute break. Everyone's coming back. Are we all ready?
I think we're fine.
We are ready.
Okay, cool. Okay, let's hop to it. Creating our first program. Woohoo! Unified tool chain. So we got one command here, the Go command, which you've all installed because you're all good students. And this one Go command has everything we need: built-in formatter, the builder, the compiler, and we can even build for other platforms. Like I'm on a Mac.
Jacob, one second. Can you reserve the screen for after us or something, or?
I'm sorry.
No, are you coming to workshop?
Or for the workshop?
Yeah, just.
Okay, come on,
Yeah,
come on,
okay.
come on, come on.
We have it until 9. So.
Until 9? Okay, great.
Yeah, or 8.
Crazy. I was about to say till 9. How did you manage that?
Okay.
And then the cross compiling is built in. So I've got a Mac here.
I cannot see screen where it goes off. What about?
You can, if you have your laptop, you can go to
there's gonna be
Discord
a pull
and
in
do
the
screen
info,
sharing.
I'm just gonna buy sneakers.
You can watch it on your laptop.
I'll just get
Windows, I have no idea.
Windows.
Windows. So there's a lot of Windows laptops in here, right?
Yeah.
I'm on a Mac. If this was C, this would be a problem. Like there'd be no way for me to like build the program, and then C is not really truly portable. It's not great. Java is pretty decent. That's what it's made for. But we can actually build binaries for different platforms and architectures. Like this is ARM. These are all mostly Intel. Maybe there's a Chromebook in here that's ARM, but different platforms, different architectures baked into the Go command. Super awesome. So yeah, I'm gonna run because we're running out of time, so I'm just gonna burn through. Okay, here's our easiest program ever. Download and install Go. We've all done that. Make a directory for your program. So wherever you want to make your program, like I have it in my documents/repos folder. I also have a /code folder. I also have a /code to do folder. It's not a super great organization. But make your directory. Make hello. However you do it in your OS. How do you make directories in Windows? Is it mkdir?
Yeah.
Okay, good, because I've forgotten how to do it. Change that directory, however you do it. I think it's CD in Windows?
Yeah.
Yeah,
Okay. So we're going to initialize a Go module with the name of the module. So we're going to type in go mod, I guess I could be highlighting this, like an animal. We're going to do go mod init. So we're going to initialize our module to be hello. That's the name of it. Let's create a file called hello.go with whatever editor you want. Please not WordPad or Word. Don't use that as your editor. And then we're going to type in 7 lines here. Package main, so we're making a binary. Import, quotes, FMT, the formatting package. Func main. Every binary package main is going to have a func main in it. That's our entry point. And then we're going to do curly brace, because we're creating the block for the function. FMT dot capital P, because it's exported from the format package. Print ln, print line. So we're calling a function, and we're passing in quotes, hello, and then here, this is an eagle. I don't know how people on Windows type Unicode. You go to Wikipedia and just copy and
You
paste
go to
it.
Google search and
Oh.
look up the emoji.
Animals. I've got it built into my desktop. Look at that. I can type a zombie in.
Yeah.
I've got a Korean flag for some reason here. Oh, because I was going to Korean barbecue and Korean flag. That makes sense. So it's Unicode aware, which also includes emojis. Save your file, and then run your program with go run dot. The dot meaning here. Run stuff in this directory. And what you should come out with is hello, and it's a falcon. You can't see it because it's dark, but it's a falcon there.
Oh yeah.
Or clubbers? Yeah, that sounds right. Poof, there you go. Did everyone get that? Did it work for everyone?
Having a
Yay,
like,
thumbs up.
saving it, I think. Oh, I did Control S.
You must have. Are you in the?
If you're
right
stuck in
folder?
VI, I can't help you.
Yeah. And
Just gotta shut the laptop down. So we got two commands off the bat here. We've been running go run, which compiles it and executes it, which is great if we just want to test something out real quick.
Sure.
But if we want to actually like build it and reuse it later, we want to make binary, we use go build. Go run makes it, compiles it in temp, runs it, and just gets rid of it. Go build, we build it, keep it around. We have go install. If there's something like I remade an awesome move because I can't remember on Windows what the command for move is, I can do go install and it'll install what I just built into my path, which is usually into like go path / bin. Now it's in my path. I can call it from anywhere. So executable naming, we've been doing go run and it uses the directory name. So it's all been like actually creating a like hello binary in the background. But if we use go build -o, we can use a custom name, output custom name. We can call it anything else we want to. When we run it, if we use the default hello, on Unix it'll be /hello, and on Windows you all get a hello.exe. So if you all run a go build dot right now, there should be a hello.exe created. If you named your directory that, some of you didn't. Saw you out there. Our conventions on this are lowercasing. So we got a lowercase the package directory. We want to have a concise name, but be descriptive. If I'm writing a package for HTTP, what are we going to call it? HTTP.
What do you mean if you write a package for HTTP?
For doing HTTP stuff, for web serving, for web client.
Okay.
What am I going to name the package? What would it be named in Java? Factory adapter class, HTTP web server. That'd be like the name of the class. Just name it HTTP.
Okay.
That way, 6 months from now, you take a look at the package, you're like, what is this doing? Oh, it's doing HTTP. Pretty easy. It's also the reason that we hate things that are named like util or etc. or miscellaneous, which are all package names I've seen in the wild, because it tells me nothing what's inside of it. A package that modifies strings, reverses them, or does something with strings. What are we gonna name it? Strings.
Yeah, it's simple.
It's not hard. It's simple, right?
Yeah.
So that's really important. So something a little more interesting. This is a web server. I do wish I could get the projector to like show the widen. But here's a full web server. So at the top we're importing log because we want to log out what's going on. Then we're importing net/HTTP. It's a standard lib package because it's not a URL, and it's underneath the directory network. Not even fully spelling out network, just net. We know what it is.
Yeah.
And it's doing HTTP stuff. We create a handler. A handler takes in a response writer and a request. The response writer is the thing that we write to, it's our response going back out. Our request, it's what's coming into the handler. Then we have write, which is a method on the response writer, and we're just sending in a slice of bytes that says hello world. That's it. Now, this is package main, so this is making a binary. It's making an executable. On line 13, we're setting up our main. We have http.handleFunc, handle a function. The slash there is our path. So everything that comes into slash to root of this web server is going to be sent to hello handler. Easy peasy. It's just called. And then our last 3 lines here are a comment saying what port we're starting it on, logging out what we're starting it on, and then finally http.listen and serve on this port. That's it. That's our web server. Then we will run it. It should immediately say starting server on blah, 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 which it is. It's just like way over here. And then if we go to, I don't know what that was. Oh, it's a new tab. And I go to localhost 8080. Can I do that? Is that, okay, fine, be weird about it. Man, that was weird. Like, if I go to localhost 8080, it's hard to see, but there's our hello world. We can change this around to be hello,
UNT.
hello UNT, there we go. We'll run it. We'll get our starting server again. I'll refresh the web server, hello UNT. Pretty easy. Web serving services in general, strong suit, super strong suit. This is clear code. Everything's encapsulated. My handler function doesn't know anything about what a web server is. My handler function just takes in a response writer and a request. It doesn't know what port it's on. It doesn't know if like TSL is involved. It has no idea. It doesn't need to know. Just takes in a request, which has stuff like the headers, what method, get, post, all that kind of HTTP stuff. And then finally it has a response writer. What is writing to? That's it. But because of that, we can test it. We don't need a web server to do this. We can just test it. So next one. What about file serving? So line 4, we got our log. Line 5, we got our network again, HTTP. Line 6, we're bringing in OS. What do you think the OS package stands for?
System.
Yes, operating system. It's a weird echo in the room. So line 9, we're setting up our function again for main because this is a binary. We're setting up our main. But line 10, I've got a comment. Line 11, I'm getting a directory because I'm calling it dir name and an error off of os.user_home_dir. So the OS package has got a lot of stuff for dealing with operating systems. OS package. One of it is getting the home directory of the user. This is actually painful across OSs between the way Mac does it and Linux, and then different variations of Linux, and then Windows, getting the home directory is just different ways of doing it. So this standardizes it. This knows what operating system this is running on and figures out just the way to do it, standard. I checked for an error. So I'm getting a directory name and an error back. There may not be a directory for the home user. Like we could be running in some weird Linux system that doesn't have a home directory for the user. So it'll return an error. Now I know we're not here because I'm logged in and have a home directory, but I'm still checking this error. So I'm saying if error doesn't equal nil, so that means if there is an error coming back, I'm gonna log out fatal, what's the right way of saying that? I'm gonna unalive myself with the error. I used to have functions called seppuku at work and I got scolded for that. But that's what it's doing. We're immediately ejecting from this. If I can't find the user home directory, this program will not work. Fatal out, print the error, good to go. Line 17, we're doing our handle again, except now we're serving from root, and instead of a function we're passing in a full file server. You'll see why in a second. Then I'm passing into the file server. I'm wrapping it in a dir, the HTTP dir. I'm telling it, hey, this is actually this type. The dir name, which I got out of my home dir. So this is a string, and I'm wrapping it in dir. I'm saying this is actually this type, passing it into file server. Then the same thing as before, we're listening and serving on port 80. So when I fire that up, actually it's gonna kill, because I'm still running this on port 8080. So now I run this. Did not kill itself immediately, good start. Can I go to the, I can't go to another tab, that's so weird. So I'll go to this tab, I'll hit enter. This is my home directory. Okay, let's get to actual desktop, documents, downloads, Google Drive, idea projects, my ZSH RC file. And you notice the path at the top, it's hard to see, but before we were just starting out of slash, now it's actually modifying our directory structure. So let's get to something deeper like documents, 5G, 4 thumb drive.
What happens if you click PDF file or something like PH file?
A PDF?
Yes.
Like this 5 terms, acronyms PDF? Chrome knows what a PDF is.
Of course, and you're just gonna open PDF.
But you notice our pathing, before we had a handler function just on root, on slash. Now we moved away with that with a muxer that knows how to handle, oh, hey, we've got a full path.
Yeah.
Where in the file system is that? So it's disassembling this path that's being passed into the file server function and grabbing this off the disk. So this is a real easy way to have a file server running. Like, I mean, this is in all languages like Python, this is pretty easy to do, but it's easy to just disassemble what it's doing. We will close that again and bigify again. So dynamic HTTP. We're going back to our hello handler, but now I'm pulling something off the request. I said earlier request has stuff like headers, it's got the HTTP method. So now I'm pulling off the request dot header, so I'm getting the headers off of that request. Then I'm doing a dot get user agent. User agent is what every browser sets to tell servers, what am I? Then I'm writing hello client using, concatenating that user agent. And the same thing down below with the setting up the handler. So we run that. Yay, it's running. I fight with my UI, there we go. And we will serve that again. Hello client using Mozilla /5.0 Macintosh, Intel Mac, that's the full user agent. So we've got some dynamic stuff happening where we're grabbing stuff off of the request coming in, right? We got a guessing game here. So real easy, we got a handler function, and instead of having a separate function as before, functions are first-class citizens. I don't need to declare them beforehand. I'm just writing it right here. Func, response writer, request, curlies, and then I'm ending curlies down here, and then closing out the function. That's it, passing it right in. And I've got a little guessing game here where you add in a guess, and you don't need to do it, but that's all it's doing right there. Just showing how we can pass in a function without having to declare it beforehand. Okay, where we can go from here, we've got, I'm just gonna speed run this because we're gonna do that. Concurrency doesn't equal parallelism. This is a big, like, brick on the head kind of moment. When you go to McDonald's and there's 2 cash registers, but only one is manned, can you be concurrent? Can there be concurrent customers served? There can be 2 lines, but they're all gonna feed down to 1 cash register, right? And that's how most CPUs do work. They time slice between different threads. But if I've got two cache registers running, I can have two lines concurrently serving customers. So it does this through Go routines. It's sort of highlighted, but it's hard to tell here. On line 16, we've got the Go keyword, and then we're calling a function. This throws it off and says, go have fun, you're now on another thread. And we'll run it. Hello world. Nothing crazy here. If I change this to time sleep 0 milliseconds, on line 9, I'm declaring message. In this function, I'm setting the message. 16, I'm firing off a set message. Sleeping 0, and then printing it out. Before, I was able to, at 1 millisecond, hello world. If I run it again, it's nothing. This go set message fired off, it slept for no time at all, and then printed what was in message. That go routine that went off into the ether had no time to set message. So it was still an empty string by the time it got to here, and then exited out. And then that go routine that was hanging out, that's like, I'm setting it, I swear, just was killed. Parent process killed it off.
Is it because it's not synchronized yet?
Yeah, there's no synchronization. If we set this to 10 milliseconds, then it'll wait for 10 milliseconds, which gives it enough time to spin up that function and set it. And we get our hello world again. So to synchronize stuff, we can use channels. Channels are a great way to synchronize. They are typed, so we can't just throw random garbage into it. We can only throw specific types into that channel. A channel of integers, a channel of floats, a channel of strings, a channel of structs of your definition. And we can pass things back and forth through them because only one process can read or send from a channel at a time. They're 100% blocking. So down at the bottom, line 19, we're making a channel, just called T. And then we pass that into sum. This function takes in channel ints. And then we're looping over from 1 to 50 and summing up stuff. And then at the end, we pass the sum back into S. We pass it back into that channel. And then finally, on line 21, on line 20, we send that off into the ether. It's doing its thing. But on line 21, we wait. We're actually pulling a value off T, off that channel. We're waiting for it. It's blocking. So even though that's off doing its thing, we're sitting waiting for a response. We're not just going to exit out. We're synchronized. And we get sum 543. So no wait needed. So channels are a normal way to synchronize with Go. So interfaces. We talked about it before, we're going to talk about it more. So we define behavior, not implementation. There's no polymorphism in Go, but we do have, we enable polymorphism without inheritance. We can't have structs inheriting other structs. There's no classing, there's no superclassing, subclassing. What we do is we can have interfaces like this sounder, because I can't think of a better name for this. Usually interfaces are named after what they do. Like an interface that reads is called reader. An interface that makes a sound is called sounder. Couldn't think of a better name for it. And then we make a dog, we make a type dog. Doesn't need to be anything special, it's just an empty struct. But then we assign a method to it called sound that returns a woof, because most dogs make woof noises. I guess Chihuahuas don't. They yip. Chihuahuas would yip, yes. And then we have a function called animal sound that takes in a sounder and returns a string. It calls the sound method on the sounder and returns it. That's it. Finally, in our main func, we print out animal sound passing in a new dog. So running it, we should get woof.
Yeah.
So if we had a cat, all a cat would need to do would be satisfy the interface sounder by making a sound method on cat, and it would have return meow. And then we call a new animal sound on cat, it would return meow. That's the way it is. Behavior, not implementation. Here is a complex one, or more complex, rather. We've got a Pokemon interface, because kids love Pokemon. Kids love Pokemon.
Yeah.
There we go, better, much better. Pocket monsters, yes. We got three things: attack, say name, and type. So it's defining the behavior of a Pokemon. You can obviously get crazier with it, like with all the things they do, but we're just making it basic for now. Basic in the complex example. Then on line 14, we've got a function describe Pokemon. It takes in a Pokemon and then prints out like a descriptor name for what it does. But it calls say name, type, and attack. Because it knows, hey, these are the methods on the Pokemon. Then we create a Pikachu. Pikachu attack returns Thunderbolt, the say name returns Pikachu, and then the type returns electric. I had to look this up. The same for Bulbasaur. I don't think I said that out loud in my life. Bulbasaur?
Yeah.
Yeah, it's Bulbasaur.
Okay. We got Vine Whip, the type, and the say name Bulbasaur. And then I'm just calling both of them on making new ones and just calling them. So, bingo bango, Pikachu in brackets, because that's the way we made it up here in brackets, attacks with Thunderbolt, right? So it's just defining behavior. This is really great because now if I've got a reader interface, a file could satisfy it because you can read from a file, or a pipe, or a virtual file in memory, or a Redis connection. Lots of things can satisfy readers and you use it the same way because it's only behavior, not implementation. Which means when I do a test, I don't need to like have a fake Redis or a mocked up file system like you would need to do in Java. I can just pass in a random reader that I created. Maybe one that does success, one that does failure. And we're functionally testing this code. So we do have generics with Go 118 or a couple years ago, generics. They're not as extensive as Java generics are. They're useful for simple things like, hey, I need to sum up some ints, but also some floats. Normally this would break. Int and float are different types. You cannot treat them same. But by creating a generic function for it, by putting brackets around a constraint, I can treat them the same. Now, underneath the covers, Go knows here are all the types, float, int 64, that you have made into a constraint. So when it's compiled, it's literally just making copies of this function. So we still have type safety, we still have performance, we still have speed because of it. But it is just a nicer like sugar on top. And if we run this, yay, we got int 622 and we got some added up floats. They're treated the same by the sum function. So we've talked about structs a lot, but we haven't really dug into structs. They're the composition object in Go. They're what you're going to mess around with probably the most. I'm creating a person here. I'm naming it person. It's great to name structs after the thing they are, not just random stuff like A, B, and C, because that's horrible. And I'm giving it two fields, name and address, and they're both strings. I'm creating another struct called employee. I'm embedding person into it. So we have composition of our structs. And then I'm also giving a position string, like what role they have. Same as the Pikachu, I've got a describe function on employee that prints out their name, address, and position. but it takes in an employee. Employee embeds person so it knows how to get to name and address. It's embedded into it. And then down at the bottom, I create an employee with a person of Jane at 456 Elm Street, position engineer, and I call describe. Jane at that street works as an engineer. Embedded. Error handling in depth, we can skip, but errors are great. Yeah, we can skip error handling. Errors are great. I talked about it earlier. Yay, woohoo. I'll run it to show. We converted because it's good, and I couldn't convert elephant, so it returned an error. I printed the error out, I returned. Errors are great. Defers. So if you're working with files, when you open a file, you have to do what at the end to a file? You've opened a file, you read from it, now what?
Close it.
Gotta close it, right? That's like breaking into your brain. Well, if you've got error handling in the middle, if you're like looping over records or CSVs in the middle and you can't parse it because it's elephant, what do you do? Like you're erroring out. What do you got? Oh, you gotta close the function. Okay, well, I'll put a close there, close the file out. But I've got that in 5 more places. Oh God. So keeping track of all that is sort of painful, especially if we have more error conditions. And this is where a defer statement happens. So defer stack, and what they do is when you exit a scope, they execute in that last in, first out order. So here I'm saying 2 defers. First one's again, and then next one's world, and then finally I'm printing hello. If I run this, it's gonna run the hello and then start running the defers last in, first out. So I'm gonna get hello world again. So super effective when you're doing stuff like opening a file, immediately after, defer close. That way, anywhere I exit in that function or I'm reading, I know that close is gonna happen. I don't need to worry about it. Standard library is awesome. We've looked at just the net HTTP lib and the format, but tons of crypto, tons of everything you need modern. Obviously Fortune was not in the standard lib. We had to go to the internet to find that. But overall, standard lib contains a bunch of stuff, a lot of stuff's baked in. It is all accessible at package.go.dev. And like if we go to the format package, tags it with standard dev, or standard lib, sorry, and the docs are good. Good docs. I have to figure out how to go back to the tab I was on. Is it tab? Aha. Okay, the present tool is pretty cool. I'm actually using that for these slides.
Yeah.
So this is all markdown, and the present tool just presents it as a WebSocket from the local system. All the code where I'm doing like run, editing it, it's just Go files in the background that it's actually running and returning the results. So present tool is pretty cool. You just install it with this. It's got a format for markdown. Anytime I'm doing Go presentations or code presentations, I use it because it's real easy to just like edit code and run it right in the browser and not flip back and forth between an editor and stuff like that. For other stuff, I still use PowerPoint. Like obviously PowerPoint's still good for other stuff, but it's pretty cool to be able to just do this in the background.
I was curious how you can run code like from your presentation.
Yeah, this is it. And I'm literally just like running present.
Yeah, wow.
So ensuring software quality. So we got testing, we got coverage, we got fuzzing. Fuzzing is very important in security vulnerability testing. I would say the vast majority of Linux crypto vulnerabilities discovered recently have been due to fuzzing. And all fuzzing is defining a specific subset of values and then computing all the permutations and throwing that at your input. If you know your crypto function takes values between 0 and 65,000, well, computers can do that real simple. You typing out every single test is quite painful. But a computer can just do that in an instant, right? Computers are real fast at just looping over 65,000 values. Obviously, crypto stuff gets way bigger. And there's certain like mathematical subspaces that they know like this algorithm is weak in this spot. So they define subsets of those and then fuzz test with that. And fuzz testing was baked into Go a couple of years ago. It's pretty awesome stuff. We got in-depth profiling. When you flip on the profiler, it actually exports a web server that then has all your profiling information on a port that you can just hit. And then benchmarking, which we do a little workshop on the benchmarking itself. So here's how testing works. You have a file called underscore test with whatever you're calling it. And then you have a function that starts with test. That's it. Easy peasy, pretty simple. For more questions about testing, the Golang unit testing and mock testing tutorial is really good. It's a pretty good one. But testing's really easy and it's baked into the Go command. Just go test. I'm speedrunning to get to the benchmarking portion. So once we've tested, like how do we know what we've tested? Coverage. Coverage is line by line. Has this been covered? If you've got conditions with your branch statements, how do we know we're covering all branches? Coverage is what tells us this. Coverage is baked into Go. You run Go test and you give a profile because there's different ways of measuring coverage. And then you run Go tool cover on that file, HTML for instance, and it produces an HTML report of what's covered line by line, highlighting what functions are covering your program. And there's a good GopherCon video on it. So we talked about fuzzing. Fuzzing is also just like testing. It's pretty easy to start up and fuzz a function just with an input set. And Katie Hochman did an awesome, she's from Google, I think, did an awesome like 45-minute fuzz testing workshop at GopherCon last year. It was really great. Okay, excuse me. Okay, profiling. Like I said, we want to find performance bottlenecks. We want to figure out where our program's spending time doing stuff. Is it opening files too slow? Is it looping through? Is it allocating too slow? All we need to do is import net/http/pprof, performance profiler, and we magically get localhost, and I think on, I can't remember what port, I think it's 8,000. It starts up a server with debug pprof, and it gives you all the information in real time while it's running. And of these two, Dave Cheney is awesome. He's got some great stuff on it. Built-in benchmarking, which we're going to go into, just like test, if we give our function benchmark as the prefix, we now get a benchmark function out of it. And we can actually have it run different input sets to get benchmarks.
Thank you, Professor. It was amazing workshop on the Go language. We really enjoyed your experience, and thank you so much for coming to teach us some new stuff.